Good morning all of you. In this video, I am going to discuss about basic elementary signals, which is very important fundamental concept of signals and systems. So in this concept, along with the definitions and graphical representations of the signals, I am going to give you some further details about the signals, which are very helpful for understanding of the concepts in the signals and systems. So this concept is mandatory for the understanding of the LTI system properties and Laplace transform, Fourier transform, jet transform properties. So everywhere, in every concept, we should have the knowledge of these signals. So first, one by one, I will discuss the signals, which are basic elementary signals in the signals and systems. Here, elementary signals we call it, out of which the first signal I am going to discuss is Dirac delta function, or else we can call it as unit impulse function. This function we are representing with the symbol del of t, and it is defined as the following expression: del of t is equal to infinity at t is equal to 0, and it is equal to 0 if t not equal to 0. Fine. Along with this expression, we have to consider that minus infinity to plus infinity del of t dt should be equal to 1. So combinedly, these two expressions defines the Dirac delta function or delta function, and this function graphically represented with one arrow mark at t is equal to 0. So this is the representation of unit impulse function, because the arrow mark indicates the amplitude can take up to infinity. And we know that we cannot generate a signal with amplitude infinity, so that here the impulse signal is not a practical signal. And it is introduced for the purpose of understanding the LTI system properties or the analysis of LTI system by using the impulse response. That is why this impulse function is introduced here. Fine. And this function is introduced with some properties which are very helpful for us, and many competitive examination previous questions based on the properties of the impulse function we can observe. So I will give the properties first. Here the first property of the unit impulse function, it is del of minus t is equal to del of t. It is symmetry property. And second property, we can say scaling property of the impulse function. The scaling property is del of at is equal to, we can write it as 1 by mod a del of t. The same scaling property, second form, we can say del of at minus b, it is equal to 1 by mod a del of t minus b by a, we can write. These two combinedly we are taking as scaling property of the impulse function. And then the third property, it is the sampling property of the impulse function. This is defined as x of t into del of t. We can write it as x of 0 del of t. And one more form of sampling property is, if x of t multiplied with del of t minus t naught, we can write it as x of t naught del of t minus t naught. These two forms we are taking as sampling property of the impulse function, and this property is the fundamental basic point for the sampling theorem, which we will discuss in future. So here the fourth property of delta function is just integration of these two expressions. Separately we are taking as shifting property of the impulse function. So first expression, if we integrate from minus infinity to plus infinity, x of t del of t dt, it is equal to, we know that integration of del of t is equal to 1. It is defined here 1. That means remaining x of 0, this is a constant. So integration of left hand side expression here, it gives that x of 0. And we can take the integration of second expression, that is minus infinity to plus infinity, x of t del of t minus t naught dt, it is equal to, here also this function integration should be 1, and x of t naught is a constant which indicates the amplitude of the function, so that x of t naught is the answer here. So this property is taken as shifting property of the delta function. Out of all the properties, we can observe many competitive examination previous questions based on this property. Fine. And the last property, fifth property, is convolution property of the delta function. So we have convolution property of the delta function as follows, that is, whenever x of t convolution with del of t, we will get x of t. And second form, whenever x of t convolution with a shifted impulse function del of t minus t naught, we will get x of t minus t naught. And we have one more form of convolution property, that is x of t minus t1, whenever it is convolution with del of t minus t2, we will get x of t minus t1 minus t2. Observe, these three equations are different forms of convolution property of the delta function. Most helpful in the LTI system properties, this property. And if you observe one point here, from the properties of the delta function, we can observe that after multiplication of signal with the delta function, there is a delta function in the right hand side expression. So we will get delta function as it is. Only thing is x of t, which signal is multiplied to the delta function, does not appear in the result. That we can observe here. After multiplication of signal with the delta function, we will get a delta function as it is with the delta function magnitude based on the amplitude of this function at that instant. And if you observe, whenever a signal is convolution with the delta function, what we are getting, if you observe, signal is there but a delta function is not there. Here in the earlier case it is after multiplication the x of t is not there, whereas after convolution del of t is not there. This property you can observe here. Anyhow, here convolution goes like this, multiplication goes like this. Each and every property is very important for us. For